Unit Operation Classroom. Today we are discussing heat loss through a multi-layer pipe insulation. My name is Shekhar Bhattacharjee. A pipe with an outer diameter of 0.02 meters carries hot water. So let's assume this is my pipe here. This is my pipe here, and this is of course, the outer layer of the pipe. So this is basically metal, and we are assuming that there is a negligible resistance here, and this is giving the temperature at the outer surface of the wall. So right here, the temperature is 70 degrees Celsius, and inside there is hot water. Okay. The pipe is covered with two concentric layers of insulations, each having thickness of 0.01 meter. What are those insulations? The first layer adjacent to the pipe is made up of felt material, thermal conductivity is given, and the next layer is made up of asbestos, thermal conductivity is given. And the insulated pipe is exposed to ambient air at 20 degrees Celsius. So, as I said, so this is the inside of the pipe, hot water at 70 degrees Celsius. There is negligible resistance here. So this outer temperature can be taken as 70 degrees Celsius here. And this diameter, so this is 0.02 meter diameter. So we can assume that this 0.02 meter. So this is basically 0.01 meter. So R1 is equal to 0.01 meter. So what would be R2? Each one is 0.01, that is 10 thickness. So this is my felt material. So this is the felt material on the top of this pipe. So here, and it has thickness is 0.01. So the radius here, this would be 0.01 here, that's 10 plus another 10 here. So 0.01 plus 0.0, that is 0.02 meter, that is 20 okay? And finally, this is my asbestos layer on the top of this felt insulation. And this has also the thickness is 0.01. So basically, this is 10 or 0.01 meter. So this radius R3 is 0.03 or 30 Now, this is now exposed to ambient air, and the ambient air is at 20 degrees Celsius. So we have seen as a summary, R1 is equal to 0.01 at 0.01 meter, R2 is equal to 0.02 meter, and R3 is equal to 0.02 meter. Pipe in the outer surface is at the outer surface. This is here at 70 degrees Celsius, not here. This is outer, so this is 70 degrees Celsius. This is of metal, so there is no thermal resistance here. We are assuming. Layer one, this is a felt insulation. So this is my layer one. This is my felt insulation here. And this is thickness is this, and the thermal conductivity is given. This is my layer two. This is my layer two. And this is asbestos insulation. Thermal conductivity is given. And convection, and finally from here, what were the temperature? Finally, this is the convective heat transfer from here, and the ambient air is at 20 degrees Celsius. We have to find out what are the outer radiant heat loss, that means per, let's say, a unit length, that is per meter. So we'll find it out, watt per meter. That's a heat loss. Okay. We know this is very simple. Assuming we are assuming pipe length of 1 meter, so this L will be equal to 1 meter. So this is the heat loss to this combined resistances per unit meter of the pipe length. Delta T overall, that means the total drop in temperature. So from here 70 degrees Celsius all the way up to 20 degrees Celsius. That's my overall delta T divided by total resistances. So how do I calculate each resistance? How many resistances are there? The first resistance, of course, is of this felt material. Second resistance is, of course, asbestos material. And third resistance is the convective heat transfer resistance from here to the ambient air. And these are standard equations which are available in any book. So I've just given over there. And this is our convection is equal to 1 over 8 A0. A0, of course, is going to be 2 pi R3L, because that's my R3. That's from where this convective resistance is happening. So that's why this is 2 pi R3L. The value of H is given. So these are all given in this website, detailed calculation. So the felt thermal resistance for the felt is this value, thermal resistance for the asbestos is this value, and thermal resistance for the convective transfer resistance is this one. As you can, this is the largest thermal resistance. So total resistance would be you have to just add like in like electrical connection. So you have to these are in series. So you have to add each resistance. So the total resistance is this one right here. So heat transfer is equal to delta T overall. What is overall? 70 minus 20. That is on the pipe wall, and this is the ambient air. So this is the heat answer. That means the heat loss per unit length, 16 approximately 16 watts per meter of pipe. Uh, heat is lost. Heat is lost to the ambient air. What are the lessons learned? So this is my answer. So this is my answer. Lessons learned from this problem. This appeared to be 16 watt per meter, assumed to be very, very small, but in chemical processes, the industry pipes are very long. It could be as long as maybe 100 meters. So in that case, there will be a substantial amount of heat that will be lost. Okay. Uh, Also, just for the sake of interest, how can you find out the temperature drop across each insulation? So, as you can see, so this is my 70 degrees Celsius here, and this is my 20 degrees Celsius. So, what are the temperature drops from 70 to here? What is the temperature drop here across the felt insulation? What is the temperature drop across the asbestos insulation? And of course, from here to here, that with the temperature drop for the convective heat transfer. So for any temperature drop, it's very easy. You already found out this value Q dot over L, that the heat transfer, rate of heat transfer, per unit length, and you multiply it by that individual resistance. So for the felt, in the felt layer, this would be the temperature drop. For the asbestos, this would be the temperature drop, and for the convective one, this would be the temperature drop. So as you can see, this is the maximum temperature drop here. So pipe outer wall 70 degrees Celsius. On the outer layer, on the outer surface of the asbestos would be this drop into 70 minus 14% more than 55.26. And on the asbestos outer layer, this would be 48.26. And of course, so from 48.36 to 28.36, that would be the temperature drop from the outer surface of the asbestos to the ambient air. So just to show it diagrammatically, this is my 70 degrees Celsius temperature felt interface. Okay, and on the felt here, on this felt, so this would be 70 minus 14.14. The delta T we have calculated, so that is 55.26 degrees Celsius would be here. This is 70, this is 55.26. And similarly, we can calculate what is the value for the asbestos. For the asbestos, the temperature drop would be right here. This is the temperature drop. So this is 55.26. So it will be 55.26 minus 6.9. That is 48.36. So here it is 48.36 degrees Celsius on this outer surface of the asbestos layer. And of course, 28.36 is a temperature drop from here to here. And that brings it to 20 degrees Celsius. So ambient area. So this matches 48.36 here, and that is 28.6 as the convective heat transfer that is temperature drop due to convective heat transfer. So that makes it equal to 20 degrees Celsius. So this is my temperature profile. So this would be 70 degrees Celsius. This would be 55.26 degrees Celsius, and this would be 48.6 degrees Celsius, and of course ambient air is 20 degrees Celsius. Okay, an important and surprising lesson from this problem. Let's see what will be the heat loss from the bare pipe. Let's assume there is no insulation at all. So what will be the heat loss? This heat loss would be, of course, this A heat transfer coefficient, the area here. There's no insulation, so that is 2 pi R1 here. We know R1 value is 0.01 meter. Ts, this is 70 degrees Celsius, we know, and T infinity is 20 degrees Celsius. So if there is no insulation, the heat loss will be 9.425 watt per meter. But as we can see that by adding insulation, our heat loss is 16. So adding insulation increases the heat loss. So that is why should we add then insulation at all? This is very surprising. So let's just look at it diagrammatically. From the bare pipe, this is the heat loss. So let's assume this is the heat loss from the bare pipe right here. But if we insulate it with two different levels of insulation, the heat loss has increased. Why this has happened? So what shall we do? So one, adding insulation on a pipe has two opposite effects. One is increasing insulation increases the conductive heat transfer resistance, which tends to reduce the heat loss. So let's say if it's a pipe, if we add insulation here, of course we are adding a resistance, so that will tend to decrease the heat loss. But at the same time, when you're adding insulation, yeah, the outer diameter of the pipe also increases the external surface area, and thereby reducing convective heat transfer resistance, because convective heat transfer resistance is equal to 1 by 8A. So this area keeps on increasing as we keep on increasing uh, the insulation thickness. So that reduces. So what happens that so what happens? It increases the external surface area, reduces the convection resistance. So so again summarizing, if we add insulation, this conductive resistance of course is increasing, so that will reduce heat loss. But since the area is increasing, that will increase the heat loss. So there are two opposite effects. Okay. So for small cylinders, increase in surface area effect may initially dominate. If there's a very small pipe, if we keep on increasing the insulation, that would have the increase opposite effect. That means in that case, for small pipes, if you add insulation, then up to certain point, the heat transfer will actually increase by adding insulation. So for that, there's a critical radius insulation. So just read any standard textbooks or your lecture notes, and that will explain how we get that. So for the felt, this value is this K is given, H is already given, so that's around 40 mm. For asbestos, this is the value, so we get around 50 mm. So for felt layer, we have 20 mm, but actually this critical value is 40 mm. So it is already less. So what happens here, if we here up to a certain point, up to a certain point, if you add insulation, that heat transfer, the heat loss keeps on increasing up to the critical point. After critical point, so if we keep on adding insulation, then the heat rate of the transfer will decrease. Normally for big pipes, this is very, very small. This value is very, very small. So adding the insulation automatically decreases the rate of heat transfer. But for very small pipes, initially the rate of heat transfer increases by adding insulation. And after critical insulation point, then of course, if you add insulation, the rate of heat transfer decreases. Again, just read any standard textbook. So addition of asbestos layer also increases the heat loss. So what are the recommendations? First of all, this is that from the safety point of view, World Health Organization has declared asbestos as a carcinogen and causes asbestos. So never use asbestos. In this problem, they are using asbestos. Never use asbestos as an insulation. Okay. Uh, Now, what shall we use? We can use flexible elastomeric foam, which is very easily available in the market, or mineral, etc. This is the approximate value of K. So, if we do the critical radius value, that becomes approximately 15 mm. But the minimum thickness commercially available is 25 mm. So, for this particular tube in this problem, the actual tube outer radius is 10 mm, and you can add this insulation, so that becomes 35 mm. So critic radius is 15 mm. So this value is much higher than this value. So if we keep on add insulation, that will keep on reducing the heat. For this one, as you can see, these are the values, so 35 mm. So in that case, if we do the calculation, you will see that the rate of heat loss is 8.41, okay, watt per meter. Whereas for the bare pipe, it's 9.425 watt per meter. So so these are just additional points. For solution of this problem, the answer is 16.026 watt per meter. That is the final answer. So this value is 16.04 watt per meter.